A fair warning to begin this lesson with. Today's topic is one that personally I'm not really confident in, as in there are many points that personally I'm unsure about, and I will try to teach you what I know and what I think is true, but it's very likely that I'm gonna butcher a couple of things in here, and if you know the topic and know that I've made a mistake, please just let me know. You're likely watching the VOD. If so, put it in the comments or tell me on Discord or write me some other socials. Just let me know where I was wrong and I can make a follow-up where I correct all the mistakes. Other than that, today's gonna be a bit mind-bendy, and honestly I struggled with the concepts here a bit in the beginning because I had the completely wrong idea what they are. So let's just ease into it slowly. Remember threads from, I want to say 2 lessons ago, I think it was. It was the ability to run code in parallel, to have different parts of your code be executed at the exactly same time. And for that we had to use the class thread, or we were able to use the class thread, where we could just create a new instance, and then we could add some delegate, or we can just make an anonymous method to do something. So for example, if we simplify it and then just start the thread, in my case I will also add a, that was the wrong one, thread.join, to make sure we wait for the thread to finish before we end the main method. Now this right line will appear. Oh wait, it was too fast. You can see it. Let's do the good old read key. So there's the hello. And this console write line is now happening in a separate thread from the main thread where we're sitting at our join and waiting. This is the most direct method to control your different threading parts, your different threads, which parts of your code run parallel. This would be like the lowest level you should go when doing stuff with multi-threading. It can be simplified though. There are lots and lots of libraries that build on top of threads and make life a bit easier. A couple of interesting things. Creating a new thread takes resources. If you remember, basically in the back end, what's happening on your computer is you have the entire context surrounding your particular code. Like, where am I in my code? What are the notable variables that I need to know of, that I have to keep track of for the CPU if I switch context and whatnot. And setting up a thread, preparing all of that, takes time. So creating a new thread should be something you do, I don't want to say rarely, but with intent. You should do it because you really need to create a new thread right now. If you just want to do a bunch of stuff constantly for mostly smaller lifetime things, you shouldn't create a new thread every single time. You should reuse your existing threads. So you would not put a single write line in one thread and then create a new thread for another write line. If you want to run all of those at the same time, you would create one thread that would output all of them, or maybe a group of threads that share the burden of handling your console write line. But they would all do a bit more work than just this one small piece of code. And while you can do all of that your own, you can create your own implementations of stuff like that. There is an existing implementation you can reuse. It's called ThreadPool. Pools are a more general concept in programming. We'll run into them sooner or later again, because they're really useful. The whole idea of pools in general is that you can create an object which takes resources away, the creation process itself, mostly time. And when you're done using it, when you don't need it anymore, you don't discard it. You just store it away to be reused later. It's basically recycling, just in the programming world. It takes, of course, a bit of extra code and a bit of overhead to manage all your resources in a pool, but usually you do that for things where this bit of management is far less resource intensive than creating new objects all the time, like threads. And for ThreadPool, we can reuse threads in here by just queuing a work item, which we can also do with a static method that we call an actual method or an anonymous method, or just an expression, but I'm going to do again. Let's sleep 100. 2. That should do the trick. This will now execute our code here in one of the threads the queue or the thread pool manages. And this queue user work item means just we have queued this code here to be executed in one of those threads. So there's one large queue where we add items to. Remember, queues this construct with first in, first out. So you add 1, 2, 3, and then when you read stuff out again, dequeue, you read 1, 2, 3 in that order. So we just have this one large queue in the thread pool where we add work into, work item, this one piece of code that we want to execute. And once one of the many threads in this thread pool are available for use, once they're not in use for anything else anymore, it will just take one item from this queue and execute it in one of the free available threads. And then once that task is done, once your code completed, that thread is then reused for some other work item that's dequeued. Very simple idea. Of course, the implementation is a bit more complicated. I'm not going to try to explain that because I don't understand most of it. If you look at the source code, there's a lot of optimization and background stuff, and sometimes the source code is eye-opening and sometimes it's just reaffirming that maybe you made the wrong choice today. Oh well, red.sleep. Let's make sure we are sleeping for 1 second so we don't miss anything. State, we can just ignore that. It's the same concept we had with timers last time, but in timers where we have this idea of a state variable that we can pass into our delegate or callback for timers to pass on data. So the code itself doesn't need to reference some outside resource that it might not have any connection to or access to. We provide that data through a specific parameter inside the method. For us, we don't really need any outside data, so we'll just discard the state parameter and just have this code run. 1, 2, and done. This way, I will have the code execute on a completely separate thread. So we can actually have a look in there maybe. Let's do current thread dot name. Why not? And let's do the same on the outside here. And this is going to be 3, and let's call this code. So as you can see, we are the net TP worker, thread pool worker. This is the name, the readable name for one of the threads in the thread pool. If you look at the output 3, that's our main thread. It doesn't really have a name. Actually, we can do ID, manage thread ID. Just copy that. So this time the order is a bit different, but 1 has a thread ID of 9, and our main thread has thread ID 1. Let's call it again. Again, 9 and 1. So that's fairly consistent right now. It's likely, I'm not too sure, but it's likely just the order in which the threads get created, and in our simple program it's always the same order, so it's not really changing that much. So if you just need to quickly run some code in the background, if you don't need to wait for it especially, if you just want it to be executed somewhere, you can use the thread pool, have it queued up, and it will be done quickly. You don't have to discard anything, it's run and done, fire and forget, which isn't always applicable, not always the best choice, but it works. So for this short little pieces of code that don't really need to be integrated in your main workflow, thread pool is a perfectly viable choice. Let's go a bit further. When you think of thread pool as using threads in the background, so building on top of threads, then we can also build on top of thread pools. Go a bit more abstract. And for that, there's a class called Parallel, which has a couple of different options, but the one we're looking at right now is called ForEach. And to show you what it does, let's initialize an array first. Array. Let's just use one item for now. Let's quickly make a loop to fill it. Array. Now let's do the classic one. Let's not be fancy. Array.length plus I, not IO. Fill it in. So each value in the array will have its index as value. And we're gonna fill this array into this ForEach method. And that's the first parameter. The ForEach method actually expects an I enumerable, not specifically an array. It's just convenient for me right now. But so you can use other enumerables as well. They don't always need to be things that exist all at once already. They can also be things you generate on the fly. That doesn't really matter. Which is also pretty convenient for a lot of cases. And for now, we're just doing the very simple task, the very simple version where I'm adding another expression here. And actually this time I want 2 variables. Let's just use I, that's good. And second would be state. So similar to before, I'm gonna make some code here. Let's do 1 again, but this time we add I. And we wait for another 500 milliseconds again. Then we're gonna run this code. And it looks pretty much the same as before, right? So 1 and 2 get written out with a bit of time in between, 500 milliseconds, and after 1 second, our entire program ends. Well, let's add 2 more to this. Let's look at the code again. Something you notice. I'm gonna rerun it in a moment, but first we have all the 1s, and then we have all the 2s. And if you look at the numbers where our I is, we have 0, 1, and 2, and 0, and 1, and 2. I is not exactly our... Well, it kind of is. Let's just... I'm just gonna add something to make it obvious. So it's kind of our index, so it is the value we're looking at. So I is still kind of fitting here. And we are writing code in here that's executed once for every element we get from the enumerable passed on first. So that means this code is executed once for every value, every index in our array. And state is the same as before, is another value we can pass in from the outside, and we're gonna just discard it because we have no need for it here. Just gonna run it again and see all the ones appear in one go, all the twos appear in one go. This thing will try to run this code not just for every item, like a for each loop, it will also try to run them all parallel. So all at once. This has limits, of course. Let's go up to 30. Actually, I'm gonna remove this one because we don't need it anymore. Thing is, Parallel.ForEach will actually wait for all the tasks to complete. With the thread.queueWork item, it's the fire and forget, you put it in and that's it. You have to wait yourself if you have to wait for the results somehow. But Parallel.ForEach will actually wait for everything to complete. So, gonna run it again. Something you should have picked up on. Trying to run it again, maybe this time with a bit more time in between. Let's make 1 second. It's not happening all in one go anymore. It's not just all ones, then all twos. It's actually staggered. We have some twos appearing up here, and then some more ones again. And then in the end, just again, mostly twos. That is because I have a limited capacity to run stuff in parallel. My computer has limited resources. Parallel.ForEach will try to maximize the amount of items it runs in parallel, but it has a hard limit based on my computer, so to speak. I mean, technically that's not correct because threads can exist without having the hardware limitation, without having the hardware to run them truly in parallel. I mean, the whole idea of multi-threading can work on a single CPU, but this thing will try to actually have them run in parallel, and it has an internal limiter to tell it how many items will it try to run in parallel, how many threads will it have at most running in parallel. So this thing will in the end reuse the thread pool, the big shared thread pool that you can access with ThreadPool itself, I think. It might have actually its own thread pool. I'm not too sure if they are both using the same underlying hidden thread pool in the system libraries. But it has one big thread pool it will try to use to run this stuff. And once it's out of threads, well, then it can only wait until one of those threads is available again and then queue the next item it has lined up to be run on that thread. While we're here, something I didn't show you while talking about threads. This is more low-level thing, but there's a class called interlocked, which is quite useful for multithreading, usually for very primitive multithreading things or just very quick solution. Let's say let's go to 0. So let's say I want to change the counter in each loop we go through. This does technically work. Counter equals counter, like that. Let's see if Well, let's see how well that works. So we have 30 items, so it should hit 30. It does actually. So, okay, this time it works. We do have the issue again of all of these threads are trying to hit the counter at the same time. Let's make it more clear. Counter equals counter plus 1. So we write it out more directly. I mean, it's still the same code, but well, still works out. The point is, if two of these pieces of code run truly parallel and try to run this instruction here, they will start by reading the current value for counter, then adding 1 to that, and then setting counter to that value. So let's say the first two items from array are read and ran in parallel, and both are just reading counter, which at that point is 0. They're both adding 1, which means the total value is 1, and then they set the counter to 1. So now both have run, both are completed, but counter is only 1. Race condition. To make sure that this counter is guaranteed to be the actual count, to make sure it's stable, we could use a lock, like the lock statement, the lock keyword. But sometimes it's easier to just use interlocked, which has something like increment. We can give it a ref, counter, and it will internally make sure that this operation happens atomically, as in it is essentially locked. It will take whatever variable we have and increment it by 1, and it will do so in a guaranteed atomic operation. There is no race condition happening here. So this way we can make sure that the counter will always be the right value. There are other versions of interlock. They're also just adding or exchanging. There are a couple of interesting, useful tools in interlock, which I sometimes like to use because it's very comfortable. It's the easiest way in many cases. But yeah, so that's Parallel.ForEach. Also pretty useful sometimes. Just you need to run some stuff in parallel. You want to process some data from an array or list or some enumerable, and you just want to do a quick modification on it that takes some resources, so you just want to do it in parallel. And then something like a Parallel.ForEach is maybe the ideal solution. Maybe. It depends. There are downsides, of course. If you don't make the threading yourself, you can't really control the different variables, like what is the thread priority? How hard should the computer try to solve this specific issue? And you have to take care of the exception handling. Something that I do is usually have a list where I have a try-catch internally, and I catch the exception and store them in a list, in a save, multi-threading save list. So either you have a list and lock it, or use one of the thread saved list types, which we haven't talked about. Just to mention it, there's concurrent back, for example, which is thread safe and could fulfill that role. And then once everything is done, I just check if there were any exceptions, and then I pass them on collectively with an aggregate exception. Usually. It depends very much on your use case. But this one internally uses a ThreadPool, which is also just a management helper to manage a bunch of threads. So threads combined to a ThreadPool, used by Parallel.ForEach. Now, why am I showing all of this? Well, it's because of the title of the stream /VOD/video. There is this thing in C# for a while now that shares a lot of similarities, at least when you first see it and try to use it, with thread. Like, at least when I tried it the first time, I thought oh, this is just a newer thread, like language updates, and we shouldn't use thread anymore, there's a new class we should use instead. Boy, was I wrong. I learned that quickly enough though, but yeah, task can look like thread, or can feel like threading. just different, more managed threading maybe. It's not. So let's try a little sketch. Why is it no longer active? What happened? Up, accept. There we go. It's back. I'm not sure what happened there. So, okay, let's say this is the entire program. This is basically the CPU view again, because I like it. It helps me with visualizing the stuff at least. So we have, this is our program, or at least that's the memory, and then we have a program that goes to different cells in here and then maybe makes a jump to this cell, and then the next cell maybe goes back, and then this goes forward and this goes forward as well, but then this one jumps to here, and all the while you have another program. This is one just running its thing here, maybe doing nothing with jumping around or anything. And that's two. And these would be two threads. They're in different parts of the memory, but they're both just one continuous line. They jump around where they are in memory, but they're continuous lines. And each of these are or represent a thread. Each of these have their own program counter and some other registers maybe. Depends on the architecture of your CPU. Many CPUs, or at least modern CPUs, actually have multi-threading built in, basically on hardware level. Plus you have, of course, the whole thing about we use multiple cores nowadays. Like multi-core is the default. Unless you're talking about microcontrollers, and I think even in microcontroller world, we have multi-cores now quite often, I assume. I haven't programmed for microcontrollers in, God, wait, it's 2025. It's almost 20 years. Maybe I should dust off some of the electronics. They still work. I don't have a flashing time. No, I would have to get a new flasher. I do know I've still a board in here. And some electronics. I could hook them up again. Sorry, getting distracted. So, yeah. These are sort of our threads. And these would be what we can think of as the C# thread class. It's this thing that prepares all of the registers and all of the memory management and points to a piece of code or an address in our memory address where we start running our code, and they keep track of where we are currently in our code and some additional important values maybe for processing in the CPU. Task is not quite that. Task would be just this line, so to speak, or not actually this, partially this line, but task would more importantly be just this section in our code. The actual code we want to execute. So it's like a smaller part of thread. It's still the code that we want to execute, and it will still keep track of where we are, how far we've progressed in the code, but it doesn't actually do all of this stuff, like the proper initializing and preparing the computer and talking with the operating system to have it actually run. It's just the whole, what do we want to do? Like, what is it that we want to work on? What is our task? That's where the name, this is the task we want to work on. It's not the infrastructure around it to run this task as well. That would be thread. A thread would have knowledge about the task it's about to do, and it has the infrastructure to make that work happen. And task is just what do we want to do? And so while task is technically often used for multi-threading, because it's very convenient for that, it's not necessarily multi-threading itself. Like, you can use tasks without having any code run in parallel, having everything very synchronously in order, one by one instruction at a time, all the while using tasks, and later on async await as well. And async await, those are two keywords. I'll actually just quickly write that down. We have task, which is a class in C#. Yeah, let's just quickly import that. We have task. Let's just do it like that. And we have the keywords async and await. And usually you would find them combined, async await. If you look them up online, it's async await is the general term. They're keywords that let the language itself interact with task, with that class. In your version there's also value task, which is basically task, but task is itself a class, whereas value task is a struct, a value type, and you can improve performance in some situations, but there are gotchas. There are things that don't work with value tasks that you have to look out for. And so if you're not sure what to use or how to react, always just go for task. Like, optimization can come later. So I'm not going to talk about it either, because I don't understand all the implications myself. The only thing I know is that while task sort of stores the result, you can constantly reuse it. Value task is once I read the value, I have to discard it entirely. Which works sometimes and sometimes it doesn't. And yeah, task is the big class, and async and wait are two keywords that let the language interact with it. It's similar to how the using keyword can be used to interact with iDisposable, the interface. We talked about that already. In the same way, async and await interact with task. Now, how do we go about this, actually using this? Let's start with a very basic. I'm just creating a static method that will give us a task. Task, create task. Now, this doesn't make much sense what I'm doing here. You will understand soon why, but we can do that. We can return a task, and actually I'm going to use completed task, which is a static value we can just access from task, which is just a task that is already completed. So I mentioned earlier, task is the actual work we should do, and it sort of keeps track of how far it has progressed. So the through line, the continuous line that's going through the memory code, we do know where we are in that piece of code. And so we know when we are finished and the task is done. And once we reach that end state, our task is a completed task. Let's get create task. Let's do it like this for now. And task, let's ignore the completion here. We can, for example, request the status. I'm just gonna write them out like this. There are a couple of different states a task can be in. The one we expect for a complete task is ran to completion, because these are basically the three states we would be in if the task is done. Like, if there's no more work continuing here. This would be, we just created it, or we're waiting for it to start. Basically, we initialized it, running is, of course, the main state we expect while the task is still running. And waiting for children to complete is, well, it's technically running, but it's not doing itself anything. It's waiting for some other tasks itself. It's like you have a child that is doing some work and you wait for your child to continue, and that child itself has some children, some other tasks that are doing something, and it's waiting for those to complete. Complete hierarchy, top to bottom. You can simplify this a bit by just going task. Wait, why is it not? It's completed. Like that. It's completed would just tell you if it's one of those 3 last complete states, which can be that it just ran to completion, the one we expected, or it can be the state it's faulted because it takes an exception, it aborted because something went wrong, or it can be it stopped running because we explicitly told it to stop, which is something cool tasks sort of can do that threads can't. But that's actually kind of cheating because tasks themselves can't really stop themselves. We can just write code that can stop, and we'll get to that. Now, task itself is just some work that has to be done. If we create a task, that's just that. It's more like a delegate than it is like a thread. That's maybe the best way to put it. Like, what you can put in your head is, or think of in your head is, a task is a delegate that also has an internal meter of how much of our method is already completed. And you can pass around a delegate that already has started working. Sort of. The other way around it would be like a thread without the infrastructure, so you need to slot it into an actual thread somehow and have that thread run it a bit further and then pick it out of that thread and wait for a bit and then put it back into a free thread and have it execute a bit further. And to do that, we have special thread pools, which you would call TaskSchedulers, which is also a class. Of course, there's a class, TaskScheduler. We can just get the current scheduler, for example. There's a default TaskScheduler, which is also associated with the default thread pool, I think. At least it is in my head, it's always the same mega thread pool that's used for everything, but I am not sure which processes actually, or which parts of the system have their own internal thread pools that are shared with everything. That's one of those things where I'm not too sure. So in theory, TaskScheduler can execute a task, but there's no direct way for you to put it into a TaskScheduler. It's a tool that is used for tasks, but not a class that you use for tasks, if that makes sense. So we have an ID here, and the other thing that you can get from TaskScheduler, not ID, this value, maximum concurrency level, which is basically how many threads does it have, if we simplify it. Very much simplify it, because the number of threads it has isn't exactly constant. A TaskScheduler has a thread pool which can expand. So in theory, it can add more threads once it knows that I have too much work to do and not enough threads to process it all. And in theory, TaskScheduler can also reduce the number of threads it has. Once it realizes I don't have much work to do anymore, I'm releasing some of those threads in my pool permanently to free up resources, because I don't have a use for them anymore. Right, so that's the thing you can do. And TaskSchedulers, you can reuse the standard one, but you can also create your own ones. And it's actually not too much work. When you create your own TaskScheduler, you're actually implementing also your own thread pool internally, or you have the option to. which is sometimes quite useful if you need specific properties to apply to the threads, the actual C# threads that are used in the background. I had a case where I needed single state apartments, STA threads, and the default scheduler uses MTA threads. Don't worry about the terms if you have never heard about them. Be glad. It's mostly... Let's see, I had that for UI, of course, WinForms or WPF, more specifically for me, and for COM interactions I had those as well. That's it. And yeah, for that I needed specific task scheduler that used STA threads, so I had to make my own task scheduler. But luckily it's pretty easy. The base classes already handle most of the stuff, the heavy lifting, and you just have to implement basically the part that provides the threads and the thread pool. Getting off track. What I've created here is just the complete task. A task that doesn't do any work, so we don't have to put it anywhere to run it. What we can do instead is use a shortcut similar to the thread pool earlier. Task.Run. To have some code that is run in the background, like so. We return that. So if you think of Task.Run being the equivalent of ThreadPool.QWorkItem. So and then let's just copy this code. That has a state that we discard. But think of these as the alternative version of that. We just have this piece of code that we want to run and we put it on the next free thread in this thread pool. And Task.Run is doing the same. Task.Run is using, at least in this version here right now, the default task scheduler, which internally has a thread pool that accesses. And it will make sure that this code is wrapped inside a task object. And it will also, at the same time, start running that task. So it's not just creating the object, it will also start it. If you think of thread in the beginning, we had the thread constructor, we created a new thread, and then we had to specifically say thread.start. We don't have to do that here. Just like with the QWorkItem, we just provide the code, and internally it will make sure it will be passed on to a thread somehow in the end, and start it and execute it. Only for the QWorkItem, it's really just a fire and forget. Once it's here, it's done. Take care of it yourself. In this case, however, because it's wrapped inside a task, we can return that task and we get it up here. And this task, when we check the status, it will actually show different values. So let's make the original code basically. Let's do another thread.sleep 500 2, like so. So some time passes, we create the task up here, which just means we internally have the task be created in the background, have it started, and then get a reference to it so we can access the information about the task. We can check how far has this progressed, has it finished? And let's just see status, task.state, status, sleep. Let's just wait 10 milliseconds. And then let's wait 600 milliseconds. Honestly, I'm not too sure how fast we can catch it before it actually starts running. Yeah, no. We didn't see any of the creation or otherwise states. We're too slow. Yeah, can skip these two, but the important part is state is running. and then you see state ran to completion after the thread outputted the 2. So we can check how far this has progressed by just looking at task, which is useful, but this is only where we start. And this is just essentially how we go from just ThreadPool to task. It gets a bit more interesting if I think about, I don't want to have a thread.sleep. I don't know how long this task will take. Right now, I know basically how long it takes, because we can assume that this is taking no time at all, so it will be just 500 milliseconds, give or take a couple of milliseconds. So 600 is well above the threshold how long the task will take to complete. But I want to be sure, I don't want to waste any time, but I also don't want to accidentally continue my code up here without the task being finished. I want to wait for the task to complete. I want to wait for it to reach status completion or wait to task.isCompleted equals true. And we also looked at synchronization methods for threading, and we could use something like an event wait handle, right? We create an event wait handle that we pass on to create task, and it will then use that wait handle to signal us outside here that it finished, so we can just wait for that wait handle. If you remember, we would have something like event wait handle.wait1, which will block the current thread, similar to sleep, but not for a certain time, but just until a signal is given. Task has that built in already. We don't have to provide an event wait handle ourselves. We can use task.wait. Now, I want to be clear here. This is not a good solution. This is not the way you should do it, but I'm building us slowly up. This is in theory what we can do. Run to completion by go for 100 milliseconds. It's pretty quick. If I wait for a second, it takes a bit longer, but we always make sure task.wait will wait until we hit is completed. It can also fail, by the way. It doesn't need to be that we waited for it to finish successfully. It's done. It's not executing anymore. It's one of the 3 finished state. We canceled it specifically, or it faulted in some way and stopped running because of an error, or it just finished normally as expected. Now, the reason I say this is not the way we should do it, this is dangerous, is because we kind of lose information, potentially. Let's make a try catch here. Like that, and sets a breakpoint, so we definitely know something happened. And throw new exception error in our method. Okay, so if you remember what I told you about the timer last time, it's running in a background thread, and if there's an exception in the background thread, we wouldn't catch it in our main thread normally. But we're using currently task, which is a bit special because we have this task that is wrapping the entire method, the code. We do have a link to it. We are still tied to it somehow. And while we are in this wait method, waiting for the task to complete, all the exceptions that come out of this code directly will be passed on as if they are thrown by this wait itself. Even though technically this is a separate thread from this one. Now if we look at the exception itself that we got here, can I open this and you can see it? You can't. Oh, can I increase the size here? Can't see the tooltip either, right? Can I copy that out? Okay, that's good enough, I guess. Just look at the ads. So this is the first tick trace. And yeah, the path separators here are escaped, of course, still. Just ignore that. It's normal quotes here. And it says we had an exception in line 15. Okay, here. Because that's where the exception was thrown. That's correct. Let's see what happens if we change this a bit. And remember this part. Instead of wait, we can go for get a waiter. So instead of waiting ourselves, we let some other system handle the actual waiting. Think of it that way. And I'm using get result. Now this is going a bit further than I want to, but tasks don't have to be just this is something to do. They can also be functions. Tasks can give us values back. We'll get to that. But for now, get result is just used as the equivalent of the wait before. So instead of task.wait, we do task.getAwaiter get result, which is more effort to write out and seems like this. Why? Let's just cause the same exception again. And copy this out. And this is not the code that I wanted. What did I make? I made a mistake. I'm not sure what mistake. What did I mess up? This is not. I'm sorry, I made a mistake. I do not know which one. This should not have been the result. What have I done wrong? A lot, probably, but... Or was it because I didn't do the next part? That might be it. Was I packaged it like this? Okay, let's retract this for now. And maybe let's get back on this later. Let's compare them again later. Just ignore that for now. Keep it in mind. I mean, obviously now you know there's something about the stack trace that changes, but okay. Let's just go back to wait. We can wait for the task to complete, and then we can continue with our main code. So far it's like we have a ThreadPool task that runs our code in the background, that includes an event wait handle as the state variable, so we can explicitly block our main thread until this background thread is completed. And that's what we have so far. Now, Task.Run is a shortcut. And just a quick, okay, I have this extra code, these couple of lines of code, or maybe just a separate method that I would just want to put that in a task, run it, give me a reference back to it. Quick and dirty, wrap it, done. And that's quite often what you want. It's a quick, short method and a good way to use tasks, at least in my opinion. There are a couple of things which are just, this is a 1 or 2 liner, done. There's a different way you can create tasks that might actually be a bit easier, depending on your context. See, I can actually ignore all of this here, just write out the code in the method, and still have this be a task. The issue that you should pick up on is this returns a task, but nowhere in my code am I returning a task. That is a problem. And that's where our first keyword comes in. Async. Async is a hint for the compiler that this method, or the code in here at least, is not supposed to be a direct method call, but instead a task. So what we did here is basically with the compiler, when we run create task, we want you to do the same as Task.Run does. We want you to wrap all of this inside a task and return that as a reference we can access. Now this doesn't really make much sense. That's why currently this is underlined in blue. But it's possible. Like, we can absolutely do this. This is perfectly fine. The logic will work out, but it's not really a smart idea to do. And just wasteful in a way. I'll just call the same code now. Well, let's just ignore the exception for now. And this should still work out just the same as before. Well, almost. Something you should see now is the 1 and the 2 happen before we get to this wait. So this console write line happens after this task is completed. What we basically told the system is that we want to wrap all of this inside a task, and we want it to run this task. So all of this code is wrapped inside one task that we get here, and it's started by the runtime. But unlike the Task.Run, the task is not executed in the background. And that's why this doesn't make sense right now. We told the system to wrap it in a task, but we didn't tell it to execute this in a specific background thread in parallel to our main thread up here. And there's a subtle difference. Task.Run will in the end just pass on the task to a background thread, available thread somewhere on the ThreadPool in the TaskScheduler, and then return the task reference. The task itself will be executed all the while on a separate thread. And your main thread just gets the reference to the task and then continues its own thing in parallel at the same time. But if we don't use Task.Run and just call the method, we're telling the system, run this code like a method, even though it's wrapping it in a task and it's starting it, kind of. It's not doing that in a separate thread. It's never calling any background threads. It's using the thread we already have, the one we're currently in. And it's executing all of this synchronously. So whether or not we create task and get the reference back, or if we just create task as pure code, as a void method, doesn't really matter in this case. This async doesn't help us. It's wrapping everything in a task, but we don't gain any benefits. We can get a benefit if we don't sleep in here. See, there's another function in task, not run, but delay, which is kind of like thread.sleep. It would be the equivalent for the asynchronous world. Let's do task.delay 500. can see that this is also not getting a blue highlight. Because Task.Delay is essentially creating a task that is run in the background, like Task.Run, and that will just thread.sleep, kind of. So it's a bit like, it's not exactly that, but it's a bit like having this code. We use task.run like we did before, and inside this task we use thread.sleep. Like this task, the only purpose this task has is to wait for 500 seconds before it completes. And we have that executed in the background on some other thread in the thread pool, and we get a task back that we can use to check, has this task completed? Like we could do .wait on this, and then we have basically thread.sleep again. Only the thread.sleep happened on a background thread. And instead we can just do Task.Delay, which is a bit more optimized. It doesn't waste just any threads for this. Not directly. It's a lot more friendly in terms of resources, and we can wait for it. Like you can with any task. So I could execute this. It hurts me to do, but we can execute this. Nothing really changed, because this is not much difference to thread.sleep. It really isn't. But instead of waiting, we can do something weird with a special keyword. We can, instead of waiting for it, we can wait it. You probably write it correctly. Await is a keyword we put inside our code itself, and we put it in front of a task. So we can also... So what I mentioned earlier about using and I dispose, this is how await and task combine. You can put the keyword using in front of any reference, in front of every variable that is idisposable, and you can put await in front of anything that is task. And async is basically only required to mark methods like this to the compiler. Methods by this means methods that contain the await keyword. So I could leave this out, but then the await doesn't work anymore. We need to specifically mark the method itself as I'm asynchronous, which only means internally we have an await. We await something. And if I run this code now, you can see we have the one output first, but then our code up here continues with the output for the status. And then we wait for 500 milliseconds, and then we output the 2 and the run to completion state. Let's try that again. This time with 1 second difference, more obvious. This wait has a special power. Basically, we have split our code into 2 parts with this. Whenever you see an await inside a method somewhere, that means this is a separation of the code. At this point, separate all the code that follows after from the code that was happening up to here. And this would continue. By the way, let's just simplify this a bit more. Let's just directly put the task delay in here. Make this a bit easier. We can let's do it like that. Put on a 3 in here. We can make a second await. First one, second one, third one, run to completion. Now we have split the code into 3 parts. The first part up here, from the start to the code until the first await hits. Then this part in between the awaits, and then this part down here after the await. I mean, technically this counts towards this code as well. So we have this block up here, this block up here, and then this block. 3 parts of the code. Let's ignore the last one. And the compiler will actually look for async methods and create a custom class for that. So what's happening right now when we compile, the compiler will kind of ignore create task. The finished code will not have this method create task anymore. Instead, it will have a special class it will create, specially named class, one that you can't really access yourself, or shouldn't try at least. And this special class it creates will have 3 methods. We will have this code in one method, and then this code in one method, and then this code in one method. So a bit like, I'm just paraphrasing right now, okay? This is not how the class actually looks. But you can think of it like that in a way. Public, whatever. Public static. Wait. 1, which will have this code. And 2 will have that code. And 3 will have that code. And then we have a private and state. Starts at 0, and then this one good state. It's 1. Oh wait, it's not static. Sorry, that was my bad. Not my bad. State 0, state 1, state it's 2. That, and state equals 3. We could actually make these private as well. No point in making them public. And make this one public. Public, void, run, and then okay, 0, 1. Case 1, 2, break. Case 3, 3, break. Right. So roughly this would be what happens. This method ends up as a class like this, where our code is split into its different parts in form of individual methods that all do just their few lines and advance the internal state each time once they're completed. And that allows the runtime later on to execute this method piece by piece. We can execute this first part, just running this one method and have it be completed, and then the code will not do anything anymore until we hit this run again, and we try to run the code again. And then a third time. And once we hit a third time, it's completed. Actually, we can set 1, 2, 3. This would be 2, not 3. That was my mistake. And 3 turn true. I can type. False. Yeah, let's make it return Boolean. False. False. Okay, let's simplify it to this. So I can just run the run method, and the return value will tell me if the entire process is completed, if we can stop now, or if there's still more work to do. So we just run it once, we just complete this one part of the code, and then we know returns a false, we know we have to execute it a bit more, so we run it again and execute some bit more, set the state to 2 and return a false because we still got more to do. Then we execute the last one, set the state to 3, and now when we run it, we know, oh, state of 3, we're done, there is no more work. You can end now. I mean, technically you could make this like this, I guess. No, that was... default. Yeah, that would work. And this allows the computer now to do the sounds very German. The one very special thing. It can offload the work to not necessarily a thread, but some other internal hardware process that can still be seen as sort of work being done in parallel, but not necessarily. On practice for us right now, that would mean, for example, this Task.Delay. That can just mean, hey, have some of your background processes just include us in their timing. Like if you have an internal timer, some clock somewhere, just include us insofar that once 1000 milliseconds ticked off, wake us up so we can hit the run method again. So we execute our first piece of code, hit this Task.Delay, which is a special task in the background that just waits for a specific amount of time before the task is completed. And because of this await, the system will just stop executing our code here. Just only do this. It will just stop doing anything else anymore until the task that was returned is completed, until we get the event from this timing system internally. And once this event comes in, it will trigger some part of our task system to hit the run method again, to have the second piece of code be executed, which then also creates a new task that hooks into the internal timers, which may be just some CPU clocks in the background, and they will then, once they're completed, complete the task, and the wait will just make sure that once that task we get here is completed, we will get woken up again. The special class will hit the run method once more, and we're going to M3, executing the last piece of code. And with that, the task is actually completed, and we just return a true, and whoever called us knows, okay, this task is now completed. So the task we have up here is actually more like this entire class, and as long as this run returns a false, we will just hit it again and again and again, and that will happen internally. We don't see that. All we see is this code that awaits another task internally. And it just means, if we put it in a less specific term, if we try to be more abstract, we split our code in parts because we have other processes we ourselves need to wait on. Like, we can do things ourselves directly, synchronously, but then there are things we have to wait on, like this countdown for 1000 milliseconds. And because we don't have anything useful to do while we just wait around for this countdown to finish, we just let the computer know through this combination of async and await. And the computer then can use this time that we wait to do other stuff. We can use its resources for something more useful. And so it will just, okay, continue running our code somewhere else, whatever else we have to do, until at some point this countdown is reached and we get a little wake-up call, and the computer now tries to run our task once more. And it's, oh, task is finished, we can continue with our code. We have awaited the end result. We can now check the end result if there's something useful this task has done, but for us it's just a delay. We just wait for the signal. So we just continue our code after 1 second. And then with the second task delay, which just hooks into the internal timers, creates a new task that doesn't complete until the timer is done. And the await will just wait for this task that we create to complete. This await doesn't hook into the timer. This await is not waiting for the time here. It's waiting for the task we create to complete. Doesn't matter what task it is. In this case, it's a delay, as simple as that, straightforward, just waiting for a certain amount of time. It can be something completely else, including our task that we have created up here. So instead of Task.Wait, I could just go await task. If I have caps lock off, like that. I can do that. Of course, I have now used the keyword await. That means my method has to be declared async, which luckily can be done in newer versions of C#. We can make the main method itself async, just to make sure that I return task and not void anymore, because this itself is now a method that's split into parts. We have this code up here, and we have this code down here. So we execute this code, and then we hit await, which means wait for this task to get set to complete. And up to then, do nothing. And once you complete it, you can try to continue the next block in our code until we hit another await. So if I run this now, the end result, we hit 1 and waiting for activation. So we hit the first 1 and then hit the delay. And because we awaited, that means we can just continue with our code up here. And we await this task as well, which will internally, after 1 second, write the 2 and then wait another second and then print out a 3. And then the entire task is completed and we continue here. Print out the 1 and continue in the main thread all the while. Then the main thread decides to wait itself, and so we just have the create task that outputs 2 and 3 with a bit of timing in between. And then that task is finished and the main thread can now close off with this last run to completion. But to return this to the original, we don't have to do that asynchronously with the await. Good, but we can use the Task.Wait that we did before. That is perfectly fine. Basically the same result for us right now, because there's nothing else we do. This is the main method itself. There's no one that can do any work when the main method is waiting for something eternally. If we hit await in here in the create task, that means we can do work up here in the main method, the one that called us. But if the main method hits await somewhere, well, there's no one high up in the hierarchy that can do something. So whether or not we do something synchronously or asynchronously, so if we just hit Task.Wait and block the current thread until it's finished, or if we hit await and technically free resources to something else to be done, it doesn't really affect it logically. It's a different process internally, certainly, but it's not really affecting the flow of our program much. But maybe this time we can see the result a bit better. Let's try throwing something again. And let's try the await first. And just the wait. I should probably add the breakpoint. Oh wait, no. Let's do red line. Let's try to be smarter this time. Stick trace. So this is the stack trace we have now. This was with Task.Wait. Right, let's try the async task. Let's try awaiting it. Await task. The asynchronous way. Yeah, no, don't care about that right now. Now we get this stack trace. Looks a bit different. And now let's try to get the get awaiter, get result. I mean, you can see the end result of this. GetAwaiter.getResult looks suspiciously closer to the await than it does to just straight up wait. When we look at the code more directly, we have for Task.Wait, the one you should not use. You get this stack trace, which is just, okay, Task.Wait internally had some issue. These are just system threading, has nothing to do with our code directly, it's just where it happened. And line 16 in our code, which is the Task.Wait. Yeah, sure. Doesn't really tell us where exactly the error happened. Like, we only know that's where we had to wait for the task that had the exception. If we wait for the task itself, if we use asynchronous programming, we have line 17, so still at the lowest level, the line where we awaited the task, but above that we didn't see the task.await, the internal system libraries. We actually saw the line in our code, line 45. That's interesting, isn't it? And if we use task getAwaiter.getResult, we still get the lowest line, line 18, sure, and we get line 50 in our code. I mean, the lines aren't exactly the best, but the important part is what you got here is actually stack trace that goes into the code itself that had the exception, into your own code, where the exception originated. It was here in the create task method. That's the important bit. Both in the await and the getAwaiter getResult. So you can do it asynchronously by using an await itself, or synchronously by using the awaiter as a helper. Both will tell you where inside the task itself it happened. It will try to give you stack trace inside the source, inside the original source for the exception. Task.Wait itself will functionally do the same for us, in terms of just the code waits on this point, but it will hide the internal stuff. It doesn't mention create task anywhere. It just, oh, the wait method failed, that's it. Wait method is wrong. And so, okay, so threading.task is broken somehow? Is that what we learned from this? Well, no, of course not. We have an exception down here in our code. We just don't see it. At least that's the explanation I got, and that's the reason I avoid it, but Task.Wait, don't use it. If you really need to just wait for something synchronously, if you don't want to use await, and just have a void method, for example, just use getAwaiter getResult. It's a bit more work to write out, and you have to remember that, but it's a lot more convenient. It will save you a lot of trouble. So with that out of the way, let's expand this a bit. I mentioned that earlier, that getResult, we're looking a bit ahead here. We're looking at getResult because tasks can't just be a task, they can also be functions, which means we can get data back. Task and value tasks as well are also available as a generic class that provide a return value. Can return an integer, for example. I have to provide, of course, the generic value in here and in here. This is a different type than just task. Task and the generic task are two different classes. Task is for, this is more like an action, like a delegate that just does something and you don't care about it too much. You don't get any value back. And the generic task is like function. It's you return something, you have something be done, and the end result is important to you. And instead of having some shared memory address that you just can access once the task is done, you can use this to directly get the data back. It's just more convenient. And we can return 10. Let's say 10. That is. Oh, let's try to be creative. Laytime.btcnow.ticks and change this to long instead of int. So this time we get actually an interesting value back, somewhat interesting value. Well, this task, to get the data, we can use either the getResult, which now will actually return a long. And we have, this is getResult that returns it. We have first the waiter, which is one thing. We have a task waiter now, and this task waiter will have a result, or will with getResult wait for the task to complete and then return the result it has. This is one way to do it. Let's call this code. And that's certainly a number. Just look at the last few digits, maybe 4877 or 114,877. Let's try that again. Definitely a different number. And if we make it asynchronous, single task, that, and use the await keyword, we can do it like this. So before we just had the wait task, which we can still do, but this itself is a statement sort of that can give us data, the return result. And we can do this as well. And we get another number, the number of ticks. So now you might be wondering, when should I use this? And the answer is when you have async libraries, or when you are creating your own async library, or if you are trying to make some complex parallel processing happen. Maybe. I think I can use async await to just structure my program a bit differently, but essentially have all the code be synchronous. That doesn't make sense. Where you really get the advantage is when you have libraries, if you have external code that has return value task that allows you to make use of these asynchronous features. There are a couple of libraries we have looked at that do actually have asynchronous versions. And that can do a couple of cool things. So let's just change this code out. Oh, yeah, let's do this one using file stream. New file stream. And path. What did I do last time? C development? Was it that or was it D? Development? Development. Yeah, okay, that was the file last time. That's our path, and file mode create, write, no shared data, like that. Right, so in file stream I could just write and just create byte buffer equals new byte. For int it's 0 less than buffer length is high. Okay, autocomplete is sometimes useful. And just write out this buffer. Okay, so we're just writing out this 1 kilobyte of data into our file. And right now there's no async stuff happening here. We're using the async keyword, so the compiler will still create the special class. It's just that everything happens in one method internally, immediately, synchronously. So the entire task will complete and then we just hit the output here, and this will not await anything anymore. We're just done immediately. And it's pretty quick, of course. Like, we're only writing out a kilobyte of data, that's nothing really. And I don't really want to make this longer. I don't want to exert the stress on my SSDs just for demonstrating some timing issues. Thing is, FileStream doesn't have only write, it also has write async. There's a convention that you don't have to follow, but it would be a good thing to do. When you have a synchronous method, just straight up boring method as you know it, you just write out the name, usually. Whatever method name you desire. But if it's an asynchronous method, you have the async keyword, you add that also in the name itself. The compiler doesn't check that, it's not necessary, it's just a naming convention. So in this case, we have in FileStream the write method and the write async method. They both do the exact same thing, it's just write will mean we complete the write operation, and until that completion is happening, we will block at that line in our code. We will wait for the entire data to be written to the hard drive. Write async will put all of that in a task. And in the background, what happens is the computer can actually offload that work from the CPU to some memory controller. And so you don't actually have to use a separate thread really to keep track of how far the copying process happens. So, I mean, there will be still oversight from the CPU, but the actual work is not done by the CPU. So in theory, you could have the write async method, which will cause internally the memory operation to happen. And then you await this task that you get back, which wraps around this memory operation internally. And it's almost like the background thread, where this operation is happening in the background, but even though it is still happening, we can already continue up here with our next line in our code. So we call create task. We're hitting all of this creation for the stream and preparing the buffer and sending it to write async. That's all happening synchronously, so we're still in create task. But as soon as we hit await, that means this task that is currently running the copy operation that's currently copying all the data from buffer onto my hard drive. We will jump back up here and continue with our code while the operation is happening in the background in parallel. So this copy operation is happening now and this write line is happening. And then we hit this await in the main method. And now we say we do not want to work parallel anymore. We want to wait for this other task to complete. Let's try to draw this out maybe. As the workflow of async await, this can be a bit weird. So with the main method, and this is now hitting create task. This is now create stream. Creating the file stream. Start copying. But then we had the await. So the copying part is still continuing, but we also hit console write line. So we have one thread here, which is continuing now. And we have a second new thread starting here for the copying. Well, not thread directly, but we have a new process starting here, running. Should have probably moved this over. But so once we hit the await, we have still the copying and the output happening at the same time. These are running in parallel. So we have multi-threading basically. We have two things happening at the same time, even though it's not necessarily multi-threading exactly. But we have parallel processing. We have asynchronous processing. They don't happen in order. They can happen even in parallel. So everything here synchronously, one just continuous flow. And then we split it off into two paths that are happening in parallel. And then we hit another await here. And what that does is, well, because we are the main thread already, there's nothing we can refer to continue. We are the main method, so we just wait. Just wait for this thing to finish. Then this ends. And we try to continue this code by using this code again. Because we waited here and did nothing, this thread was basically just idling around and waiting for something to do, and suddenly this thread is completed and we can continue this. We already said earlier we are awaiting this, so we already had the link to here. We already know at this point, look for that part up here. We were awaiting that. So once the signal came in, we move forward. I'm not sure how to draw this out properly. We created a task. That means we have a reference to this entire process here. And this await means keep a track of this process we started here. And as soon as that completed, continue our code in this thread. Just continue running this task. After we just created it, we just try to run it, and once you've run all the synchronous code, once you hit the first await, just continue here. And then wait for this other part, this background process part in the create task to complete, this asynchronous part, the write async. Maybe I'm not explaining this right, or maybe it just takes some time to getting used to. I feel like you don't quite get what I mean. That's not a good sign. Yeah, but the magic happens mostly right now in write async, because that's the code that actually causes the parallel processing right now. At least it should happen. Not necessarily. It could actually be that this is running something first and then this code continues, or first this continues, and once we hit await is only when this starts running synchronously, and it's not necessarily true parallel working, true parallel processing. But in your head it should be like, this is currently happening while this is happening at the same time. And then once this happens, we decide to wait for this to complete, so only this is happening right now. And once this completes, then also this completes, and then we just have this left up here. So this await is sort of splitting the flow of the code. It's rearranging the order in which stuff happens. We're waiting this part so we can pull up this work that comes later, do that now. And then once we hit the wait here, where we decided we can't do anything anymore, we have to now wait for the result down here. Now we can focus on completing this. That might be a different way to looking at it, maybe. Yeah. Like this part here and this part here, they can happen parallel. But this part down here, or this part as well, this can only happen after this happens. So by using the async and await, we arranged our code in these couple of blocks. This has to happen first. Then this and this, they can happen in any order they want. They can happen parallel. This can happen first, this can happen first, and this second. They can be processed at the same time. Doesn't matter, there's no dependency between them. But this code has a dependency on this code, and this code only runs after this is finished. So we first run this, then we start this, then we also execute this, and then we wait for this to finish, run this, and then this again. It's a bit weird, but fundamentally the async and await only told the compiler which parts of our code are dependent on which other parts of the code. And the different parts are just split based on method calls with the async and internally with the await. And sometimes that means code can happen in parallel, and sometimes it's happening after one another and the computer just decides in which order. It's not necessarily multi-threading and parallel processing, but it usually is. And in this case, the CPU doesn't really need to do anything itself, so it can actually offload that work to some other PC components and speed things up, so we really can process this largely parallel to this. So it's sort of like multi-threading. And there are a lot of other methods that do async operations like this. Streams are, of course, a big part of it, like reading data from disk or writing to it. Those are just very dumb things that involve a lot of external and slow hardware. So making them asynchronous so you can do other stuff while the operation is happening with some resources of your computer that you don't need for the CPU directly, that's good. Networking, a lot of uploading and downloading in the internet, or just networks in general, you have to wait for something that doesn't involve the CPU. You don't have to calculate anything really. The network controller, network card in your PC will handle all of the communication and will probably just forward it to the internal bus, which is read by some memory controller that can maybe directly put it onto the hard drive if it's instructed that way. The CPU is just idling. So stuff like that as well. Async. or the Task.Delay. If you have some internal timers that just trigger a timeout or interrupt at some point, the CPU doesn't need to wait for that and spin all the time. Waste not, want not. So it makes the structure of your code a bit more complicated, but it allows the computer to decide what to do when a bit more freely. So it can adapt dynamically to whatever situation is happening at that time. So it can see I actually do have some free time now. This is happening in the background on my system. I can execute this code already, save myself some time. And some other systems that might think, I can't really offload that. The CPU has to do it itself, so it's doing this and then this after one another. It's doing it synchronously. But you didn't have to specifically program that. You just decided to tell the computer how your code has to be structured, which parts are dependent on other parts to complete first. That's asynchronous programming. It's not synchronous. It doesn't have to be in order in this exact schedule. It has to just align with these dependencies you can indicate with async and await. And the backbone is Task, which is just the workhorse. Well, not workhorse, it's more like the saddle in which you put your load. The workhorse would be still usually a thread, but you don't see that. That's a thread from a thread pool inside the TaskScheduler usually, which you don't directly have access to, unless you make the TaskScheduler yourself. One last thing we have to discuss, it's a long episode already, but this is important. The async methods usually accept a so-called cancellation token. I'm just passing on the standard none, which is the default value also, like literally default. It's cancellation token, it's a struct, it's a value type. The default value, all zeros, is the same as cancellation token.none. It's a special tool that lets you signal systems to cancel. That's its intention. Think of it similar to the event wait handle, where you can set the flag somewhere in code and some other part of the code can now react to this flag being set. Though cancellation token is a bit similar and also simpler. Thing is, you don't wait for the token to be set, you more just check if it is set. So actually it's closer to just a Boolean variable that can be true or false. Is the flag set or yes or no? It's just very thread safe, which I guess Boolean variables are also thread safe, but only if you have direct access to them and they're not just delivered in, doesn't matter. You can still hook into the cancellation token with a special event, so to speak. You can register for callback when the token is set, so you can still react to that similar to an event wait handle if you really need to. But usually the point is you have a cancellation token from somewhere and you just pass it on. So my method, for example, has to get a cancellation token, and that's what I pass on myself, like that. And this can come from up here, and I'm just going to use cancellation token.none for now. So we don't care about that, but our method accepts the cancellation token that we pass on to write async. And write async will check this cancellation token to see if it is cancelled, which you can literally check by is cancellation requested. You check that with an if, for example. And once the cancellation is requested, it will stop copying the data. In our case, we are probably not hitting the point where we have to interrupt anything because it's only a kilobyte. It's basically instant. But on a long process, think of a download on the internet that you want to interrupt because it's taking too long. You just set the cancellation token to cancel. Please cancel. And it will abort. And this task will end earlier, before it finished. And that's what the other states are for. Remember, we had run to completion so far. but there's also cancelled, because we specifically cancelled the task, which we can't do with a thread. So if we go back to the basic structures, threads, we can technically kill them, but that's not a good idea because that can actually break parts of your code. There are a lot of safety systems that require that some code can still run, like the finally part of a try finally. If you just kill a thread, then stuff like that can't happen. And locking, for example, if you lock some, let's not get into that, but killing a thread, bad idea. Canceling a task, extremely safe, because you don't really actually stop anything directly. Anything that accepts a cancellation token will usually have the programmer put in stops in their code where they decide this is now a safe point to end. It would be safe to stop at this point, but not this other. So for example, I could create the stream and could check the cancellation token with an if cancellation token is requested, that's set, return 0. Let's not do that. Well, let's go -1, negative value. So if the cancellation token is triggered while we are opening the IO request, while we are connecting to our hard drive, then we can abort the entire process before we start filling a buffer and requesting memory and starting to write stuff in there. And we can do actually the second one in here. We might reserve the memory, but we still have a time. This could still take some time to prepare, and then during that time we might cancel. And okay, then we can cancel in here. That would be safe. Before we start writing async, though probably write async will also have a check to see if it's cancelled. So we can just leave the cancellation token in here. We might ourselves instead try to do this. You might think it's weird that we start with a cancellation token that is already cancelled, but that can happen. So having this check in the top, not a bad idea. And I could do now one down here, but at this point, there's not really a reason to. I'm just returning a simple value, and I don't see any reason to cancel the task at this point, let it complete. At least from my perspective, that's not necessary to cancel down here anymore. That would be the, how do I say, the nice way to react to the cancellation token. Not necessarily the best way to end it. This is just a very polite, I see you canceled the request, I will just end the task correctly. It will run to completion. It will have the state ran to completion after this is done, so returned, and you will have a result, though that result might be not what you expect. As long as they provide the summary for that, it's good. There's a more impolite version, but maybe the better version, and that is throw if cancellation is requested. It's also the shorter one. It's the one I usually use. No. That. And it will do what it says. It will throw if the cancellation is requested. So internally it will basically just be an if, like we had. Check if the cancellation is requested, and if so, it will create a new exception and throw it. And this new exception is an operation cancelled exception. And we can actually catch that. Let's do a second catch in here. Cancel exception, OCE. So if we have a specifically operation cancel exception, we catch it up here. Any other exceptions and down here. Just the usual catch logic. We try to pattern match from more specific to more general. If I execute this code now, it will not really do anything because our cancellation token is cancellation token none. It doesn't cancel. It's basically infinitely set to not cancel. And sometimes that is the right choice. A popular thing to do often is this. Default, said earlier, default is the same as cancellation token.none, or It's actually the other way around. None is a static field that is set to just the default value, everything 0. So I can also leave this out. That's a popular choice. If you don't have a cancellation token provide, it's just the default value which doesn't cancel. It's also what you have in here. Like, right, async has a default, there's an optional cancellation token, exactly the same as we have here. So that works. But I want to cancel. I want to get a cancellation token that triggers after a bit. Where do I get that though? You can create cancellation tokens yourself. You need a source for that, a cancellation token source. And this is a class, which do like this. You need to dispose it by using. And when you dispose it, it will also trigger all the cancellations. But you can do here is now cancellation token source.token. This token source will now provide this one token. And to cancel this token, I have to go to the source and go cancellation token source.cancel. And cancel will just set the token to cancelled, set the flag, so to speak. Until I hit this method, it will be now different from cancellation token none. So no cancellation requested, this will do nothing, this will do nothing, and this will just complete without any issues. But if I cancel, which I've done already, we hit the operation cancel exception because the operation was cancelled. If we look at the operation cancel exception, we see it has internally the variable cancellation token. This cancellation requested is set to true. And if we look at the stack trace, I'm gonna see something interesting that you have to gonna get used to. We have some weird names in here you might not recognize. Actually, I can't remember. Didn't we see them earlier already? Doesn't matter, I didn't explain that. We see move next. Move next. Even though we don't have any enumerators here, at least not visible. Create task and main, and it looks weird, right? Well, remember this special class I mentioned? Well, you're looking at them. The special class for the create task method is here just this less than create task greater than d __ 1. And move next is basically what we called run before. And because I made my main method also async to use the await here, of course we also have a special class for the main method, which is this down here. With again move next being the equivalent of the run method. When we look at line 36, doesn't make sense. Yeah, the line endings don't work out properly because I matched them with. I messed things up. Okay, so 36 in the original code. This is where we hit because we cancelled the token. We passed on a cancelled token, so the cancel was token when we run this code. Through cancellation requested through the cancellation exception, and we got it output here. Now we can decide what to do. Maybe the cancellation was fine and we don't do anything, or maybe the cancellation was unexpected and then we can have special code that handles with that case here. Usually, at least in my code, you have always 2 catches for your code if you use async await. One catch for the actual error handling and one catch for, okay, we had to cancel somewhere in our code, either directly in this code here, or maybe directly in this create task method, like so, or maybe in some deeper level, like inside the write async, if we canceled while this was running. And it just trickles back up as an operation cancel exception, and we can specifically react to that. And if we want to make sure that it's our cancellation, we could go now to oc.CancellationToken and compare that to some other cancellation token and check if that's what cancelled is and whatnot. Let's say I don't want to cancel it right away. Cancellation token can also cancel with a bit of delay. Actually, let's do that directly manual here. We have cancel after, for example, which just means cancel it in 100 milliseconds. So right now, it was too fast, nothing really happened. Let's slow the process down a bit here. Let's say, actually let's just make it simple. We use another wait here with a Task.Delay 500, which, by the way, also can accept cancellation tokens. So you don't necessarily have to wait for 500 milliseconds, you can abort earlier. We get an operation cancelled exception. Of course we did. And if we look at the stack trace, let's this time put it below our code so we don't mess up the line endings anymore. Task at line 49. Inside this task delay, which is correct. So this cancel after triggered the cancellation after 100 milliseconds. So this didn't trigger, and the write completed. And we were currently waiting for the Task.Delay with this away. And cancellation token triggered after 100 milliseconds. And so the entire operation cancelled earlier. So let's put it to 5000 so you can see it. This was not 5000 milliseconds. So it was really 100 milliseconds. Let's make that to 1 second. Trigger. 1 second later. So this is really convenient. Unlike with thread.sleep, you can cancel waiting for it. So that's another cool feature that you have with tasks. Because everything is asynchronous, it's intended to be rearranged on the fly. So if you want to abort early, you can do so. With thread.sleep, it's more of a, I know exactly I want to wait this amount of time at this point in my code, and that makes sense because it's synchronized with these other parts of my code that do these things, and yeah, whatever. For this specific case, there's a simpler way to do all of this, although I don't have to specifically call a method. I can just provide the timeout in here. Like the cancellation token source is directly built this way. It's more like a timeout in that case. So I have cancellation token source that makes sure that after 1000 seconds, this token will be set to cancel. And that means whatever task I start in here will get a cancellation after 1000 milliseconds, after 1 second. If it didn't finish by that. So this one waits for 5000 seconds. We get an operation cancelled exception. But if we reduce this to just 500, ran to completion. No operation cancel exception because the cancellation happened after all our tasks are done. We're safe. So it's like a timeout in that case. And that's probably one of the more useful use cases. There are also ways you can combine cancellation tokens. But we're not going to talk about that. Cancellation token registration, we should talk about that quickly. We can do register. And I can add a callback in here. Think of it similar to the callback for timers. We just trigger once. Oh, this is triggered once the cancellation is requested. But the important part is this will actually give us this object, the cancellation token registration. And it's important that we dispose this one. I'm not going to bother storing that in a variable. Cancellation token registration, you can dispose it, but you also have cancellation token dot. Actually, no, let's ignore that one. Let's just go for the dispose directly. And just do nope. Alright, I did have to store that. Yeah, okay. Okay, that works at least. So once my code returns, this registration will also return and deregister. This is important. Don't forget the using. You need to dispose these cancellation token registrations, but otherwise, let's just run it now. You don't see anything. If I run a bit longer, you can see in the output was cancelled. So this time the token triggered and we had the operation cancelled after that. So that's how you can react to that as an event instead of just a check if it is triggered or not. I feel like I forgot. Right. Actually, let me put the code back. So with the asynchronous libraries, there's also a new dispose you should know about. We've talked about dispose already. Like this is what I'm doing right here with the using. I'm forcing the system to call cancellation token registration dot dispose once it leaves the current scope. There's also DisposeAsync, which is not too common, but many libraries that offer dispose already have an implementation for DisposeAsync. So you can await it, the disposing. The dispose itself is a background process, so to speak, something you can delay or rearrange in the sequence of events. And there's a special using for that, and that's await using. You can only use that for objects that have a DisposeAsync method that can be asynchronously disposed. But the idea is that if you have that option, do it. Because that means the disposing, which for example for the file stream includes of course the flush operation that makes sure that all data is actually written to the hard drive, which can be a longer process. So just like the writing itself directly, or at least what we thought was the writing, the flushing, which is included in the dispose, and of course the closing IO operations, you can offload them to other parts of your computer as well, putting them in parallel to your main processes. That's why it's a good idea to use that. Only of course if you really are fine with it being asynchronous. Sometimes you specifically have to wait for it to complete. If you have to juggle a couple of resources around, just go for the normal using. Still works just as fine, just as well as before. No problem here. Let's await using. We have cancellation token. There was something else that I wanted to talk about. There is, okay, that was it. There's an asynchronous enumerable. Honestly, I'm not going to talk about that today. I'm not sure if I'm talking about that anyway. It's such a, to me at least, such a niche use. But there's an enumerable, a way to use enumerables asynchronously. You can iterate through something, but not enumerable asynchronously, but enumerator. An asynchronous enumerator, that's more like it. And you can step through that with an asynchronous for each loop, which is a very specific thing. But you might come across it. So yeah, that's this thing that exists. All right, and honestly, I think that's enough for today. There's a couple more things about async and await, but this should be enough for introduction. We're already way over time. So, your goal for your homework. Let's see, homework. See, there's a lot to unpack here. If you remember playing around with threading once I introduced that, or just because you were interested in anyway, if you used anything in parallel, if you did any multi-threading tasks, some small code projects just for fun to play around with it, try to implement those again, but using async await. It doesn't need to necessarily be actual parallel programming, like anything happening in actual synchronous or not parallel way, but just try to write your code as if it could, as if your methods are actually run in parallel. Or maybe you do have method calls you use internally that can be awaited. Maybe you have some classes already in use that do have async overloads you might be able to use. If you use anything with thread.sleep, you have Task.Delay, of course. If you have any file stream operations already, there are the async overloads for that. Actually, there are also some async overloads for example, the semaphore slim we talked about, the synchronization object. Semaphore slim also has asynchronous wait operations that await the signal from the semaphore asynchronously. So stuff like that. Pretty interesting. And try to recreate your code using async await. That should be your homework. Right. I'm gonna hope my voice isn't completely shattered tomorrow, and I'll see you next time. Bye bye.